Okay, so in this lecture we are discuss about the radial basis function kernel. So in previous lecture we have seen about the polynomial kernel. So in this lecture we are simply discuss the RBF kernel or radial basis function kernel. So let's start. So it is this kernel is the most popular kernel among all of the kernel. Just in SPM, if you just use the kernel tick, this is the most common and most popular one. Okay, among all the kernel. Sorry. If you just consider the SVM among all the kernel, this kernel is the most popular and general kernel. So suppose let's take we have two data points. We have simple if we have two data points, or you can say if you have two vectors. Let's take it is our x1 and x2. Then our kernel of RBF kernel of our data point x1 and x2 can be written in this form: exponential of minus norm of x1 minus x2 by 2 sigma square. Okay, this is simple our formula of the RBF kernel. Okay, this if you just see, this is one kind of Gaussian function. Okay, just we are discussing everything, how it is compared to Gaussian functions, and how it is important, why it is in general purpose, and why it is the most popular one. Okay, and also we have seen that the is RBF kernel is same kind of KNN, that is k nearest neighbor. Okay, first just see the interpretations. Just see the interpretations of these functions. So suppose before avoiding the complexity of these equations, this formula we have taken as the distance from the 2 points. If suppose if we have 2 points, suppose if this is one x1 point and if this one is our x2 point. Okay, and simply we can take this distance 1 2, d of 1 2. So means d of 1 2 means nothing. This is the simple norm distance of our x1 minus x2. So instead of again writing x1 minus x2, we are here using d12. So don't be confused about that. Sorry, one thing I have missed here. It will be here square sign out. Okay, so now if we just use this thing, so this formula is now converted with this one. Minus d12 a whole square by 2 sigma square. Okay, and this thing just this one, that is 2 sigma square. Here sigma is our hyperparameter, and also if you just remember the soft margin SBM, there we are using one parameter c, and in if we are taking the soft margin SBM with RBM kernel, then we have considering two hyperparameters, c as well as sigma. Okay, such kind of two hyperparameter we have seen in elastic nets, where we are using the L1 regularizer as well as L2 regularizer. So similar kind of things also happen here. Here also we have one parameter. This thing is called the hyperparameter in RBF kernel. Okay. So just I am telling this thing again, write this. If we use the soft margin SVM with RBF kernel, then we got two hyperparameters c and sigma. C is coming from soft margin SBM, and sigma is coming from RBF kernel. Okay, they are have two. These two is hyperparameter. Okay, now just analyze these functions. What is the geometrical interpretations of these functions? So just discuss one by one. So first rewrite our functions. So now our functions k of x1 x2 is now what? K of x1 is x2. We have taking this function exponential of minus d1 to h square into 2 sigma square. Okay, where our d12 is equals to norm of x1 minus x2 the whole square. Okay, just analyze one thing first. If you observe, if we increase, actually this is nothing, this is the simple distance. So instead of again speaking telling d12 I used the word here for d12 distance. Okay, so if you just increase this distance, if we just increase the distance between two vectors x1 and x2, if we increase this distance, then you see the kernel value is decreased. Then the kernel value of x1 and x2 will decreased. Okay, so simple. Why this one is decreased? If you just analyze this deeply, just I'm going to deeply. Okay, just this functions we can write as this way. This is because this exponential we have here minus, I can write this function as this formula. Okay, I can usually use this thing. So if you just see, if we increase d12, just see step by step. If we simply increase d12, then our d square, this implies that d square 12 is also increased, this thing is also increased. And if d12 increased, then what? Then if this one is increased, then it is increased exponentially. d12 a whole square increased exponentially. Just take some, for some time our sigma is constant. Let's take our sigma is constant, just omit this term. Okay, and so then if d increase, then this term is increased. If this term is increased, this mean what? This mean our 1 by e to the power d12 square decreased. Okay, because it is the inverse function of this. So if this one increased, then it will increase, decreased. So for this reason, if we increase d12, our kernel functions decreased. Okay, so in another language, if we call this one, if we just write in another language, if we have 3 points, suppose let's take we have 3 points. This one is our x1, this is on our x2, suppose x3, and the distance of x1 and x2 is of d12, and distance of x1 and x3, let's take it is d13. Then simply if d increased, kernel decreased. So if d increased, so kernel of x1 and x2, kernel of x1 and x2 will be greater than kernel of x1 and x3, because our kernel value, distance value x1 and x3 is more than, since d12 is less than d13, this implies that d greater than. Okay, I think this is clear. So if you just see this thing, because the similarity of x1 and x2 because the distance between these two things, x1 and x2, are more closer than distance between x1 and x3. So the similarity of x1 and x2 are more than similarity of x1 and x3. Okay, so if our similarity value is here, actually for similarity, actually this, if we just compare this thing, if we just similarity of x1 and x2, if we just simply just compare this thing, similarity of x1 and x2, and it is the similarity of x1 and x3, then as distance increases, our similarity value decreases. So we can call one and another language, this kernel is one kind of similarity concept. Similarity concept is kernel. This RBF kernel is one kind of similarity thing. Okay, so as distance increases, our similarity value decreases. And in another language, we call, in another language, if we just call distance is equivalent to dissimilarity. Means if our distance increases, then our dissimilarity increases, and this dissimilarity increases means our similarity value decreases. Okay, so I think this concept is clear, all of you, how the functions, these functions, how it is comparable to our similarity and dissimilarity concept, and how it is the relation, how the distance relations is related to this kernel function. Okay, this concept is clear, all of you. Now just I am using the Google. That's simple. I am going to draw this function. Okay, before going to draw these functions, here I am just change the value of sigma, and we are just interested to see if we change the value of this sigma, so the how the relations, the distance are behave to our functions. Okay, just simple. Here I am going to take, I am just interested to change the value of sigma. I'm just going to change the value of sigma in such a way that here I am going to consider three types of value. So first I am consider sigma is equals to 1. Then I am just decreasing the sigma value, that is I am taking here 0.01. As you interested, as if you interested, you can take any value that is lower than 1. And I am just increasing the value of 1 from 1, that is I am taking here 10. Okay, just I am taking this example. Okay, first I am decreasing the value of sigma, then I am going to increasing the value of sigma, and we want to see how this function behave to our distance. Okay, so let's go there. So now I am going to Google. Okay, just I am using simple, I am typing plot this function name, exponential minus x square. Simple, just I am typing here this function, exponential of minus x square divided by 2 sigma square. Simple, I am typing this. So instead of distance d12, here I am using x. Instead of d12, here I am simply using x. Okay, nothing I am changing here, I am just simply. Okay, here simple, I am in this formula, I am using sigma is equals to 1. Okay, just see this function, here. Just if you just check here, after 4 and minus 4, this value tends to 0. Okay, approximately tends to 0, but before 4 its value increasing 1. And this function is a symmetric function, so the negative side and positive sides will not matter. If simple distance is increased, positive direction as well as negative direction, it does not matter, because here simply we are using the x square term, because simply here is x square term. Okay, so it is does not matter. Just see step by step. So first one, if you just I am going to change the color. Okay, in this color. So if we first just observe it, if our distance means here it is the x value, it is the distance here, instead of d12 I am taking here x simple, this is the d axis, that is our distance. Simple, I am taking for distance d, and it is our kernel function, that it is our k of x1 x2. Okay, so first see, if it is this point is our 0 point, if our d is 0, then kernel value is what? Kernel value is appropriately 1, properly 1. Okay, if just see, if z is equals to 0, then our kernel value is 1. Okay, then kernel value is 1. Let's take another. If we simply increase the value as positive directions and negative direction, if we increase the value of d as positive as well as in negative, it doesn't sorry, it does not matter. So then you can see that the value drops exponentially, our k value drops exponentially. Okay, so if we simply increase the value d, then our k value drops exponentially. Okay, suppose, and you see that it drops exponentially, and you just see, observe one thing. If this value, if this distance is greater than 4, then this k value approximately tends to 0, approximately 0. Just see this picture. After 4, this value is approximately 0 as well as mine. Okay, just see this thing. So this is one observation. If our greater than 0, then our kernel values approximately 0, tends to 0. Okay, and see, if our distance is, suppose this is I think 1, if this distance is 0.5, then this distance, if this distance is 0.5, then our value will be like anywhere here. So actually we see that if our distance is closer and closer, then our kernel value, that is this is one kind of similarity value. So our similarity increased. If our distance decreased here, then our similarity decreased, and our distance increased. A distance increased, then similarity decreased. If our distance decreased, similarity increased. That is kernel value increased. So okay, simply one thing, if our distance equals to infinity, then our similarity equals to 0. So if you just write this thing in limiting concept, sorry. If our limit d tends to infinity, similarity of this value equals to 0. Okay, these are the both the things. I am just using the limit sign. Okay, I think it is clear. Now one thing, I'm just I also write this in our just before of this picture. I'm just also seeing here how kernel is equivalent to our similarity. So kernel is approximately equivalent to similarity concept. Okay, and our distance, just you see, at this distance, and our distance is approximately equivalent to dissimilarity. Okay, dissimilarity. I think the picture is clear. If you just think this thing, if our dissimilarity increases, similarity decreases. If our dissimilarity decreases, similarity increases. Okay, now let's draw of a fun. That just one thing before changing the value of sigma. I'm going to just introduce one thing. This function, if you just see this function, these functions would look like, this function is just look like a Gaussian function. Okay, I promise you, I have seen this is one kind of Gaussian. If you just remember Gaussian function, this is look like the same of Gaussian function. So the distribution is look like a Gaussian distribution, Gaussian PDF. So these distributions we have taken here in RDF is one kind of Gaussian probability density function. Gaussian probability density. Okay, means when our sample, if we just write, if simply if our sigma is equals to 1, then kernel is equivalent to, then our kernel is equivalent to our Gaussian PDF. Okay, I think clear all the things, all of you. Now we are just going to change the value sigma. So simple, just a simple, I am going to change the value of sigma. Here instead of 1, I am just here using 0.1. Okay, simple, I am using 0.1. So let's see what happens. Okay, just see it. So just see the breadth after when we are just see this thing. When we are using the sigma is equals to 1, here I am using here I am using sigma is equals to 0.1. Okay, when we see that when our sigma is equals to 1, so after 0.4, after 4, our value tends to 0. Okay, after 4 our value tends to 0 when sigma is equals to 1. Just here in this case we see that when we are just simple change the value 0.1, then after 1, this I think 2, this will be our 1. Just change the color for 1. I am here using black color. After 1, here 1, after 1 our value tends to 0. By simple decreasing the value, we are just simple squeezing this function. Means we are consider about our more near point. Just see this thing, we are consider about our more near point. Okay, this black color we are used for here, sigma is equals to 0.1. If we are simply using the 0.1, then see the how squeezing the part. And after, okay, so just write this thing, when our d of for sigma is equals to 0.1, d of x1 and x2 if greater than 1, then kernel tends to 0. This is for sigma 0.1. Just see. So simple, by changing the sigma value, by changing this parameter value, we are squishing this function. Means we are going to consider the more and more near a point. We are considering the more and more near point. In previous case, we are considering this distance point. The radial basis function's distance is this, but by simple changing the value, we are considering the more and more closer point. Now just we are in the next, we are just increase the value of, see, if we increase the value of sigma, just here I am using the value 10 now. Okay, simple I am using the value 10. What happened? Let's see. So it is great thing. Here our just distance value increase. Just see what distance. Just I am going to zoom. Okay, I think it is better. Okay, just I am going to here simple. I am here changing this value. Instead of here, I am here using, if we are using 10 here. Now see, I think if we move this one, I think it is better. 10, 4, okay. Just I am going to move. Point 4, I just move 0 here. I'm just moving. This is the 0 function. Actually 1 will be something here. Means after 10 means just replacing the, okay, means 10 is here. After 10 its value takes 0. After 10 its value takes, think somewhere here. That means we are just simply by using 10, we are just increase this value after something means from where. Just see this, just zoom out this picture. This is one. Okay, means something after 40. Okay, just simple. Okay, this thing, this view is okay, I think. Okay, so just see, if we just, I am here for 10, I am using here a different color, just I am green color here. So after 40, after 40, so just see this green color. After 40 our value tends to 0. So when for sigma is equals to 10, okay, d of x1 and x2 if greater than 40, then our k value to 0. Just see this thing, if we increase the value of sigma, then we are simple, just take consider the far and far away point, taking our nbd, just compare this thing as knn. We see when our increase the value of k value, then we are considering the far and far away point. If we decrease the value of k, then we are considering closer and closer point. So simple, the same k in knn and is both the similar in our radial, sigma is both the similar in radial basis function. Okay, by simple, here we are considering by simple increasing the value of sigma, we are considering more far and far away point. Okay, just see. I think this clear is this concept is clear all of you. So let's go to our main discussion page. Okay, we actually see that, just what we will see, just redraw this. We see that first redraw our pictures in for lambda is equals to 1, or lambda is equals to 1. Yes, draw it. Or we draw that for this, if this is our 1, we see that when actually this is our 4 plus 4 minus 4, we see that when this one is 0 0 0, after that it will take this kind of picture we have seen for lambda is equals to 1. Okay, this is our kernel. Just see now point 1, if we simple consider the point 1, if this is our minus 1, if this is our 1, then we see that when we considering one value, then our value is be function will be like this. Okay, and if you consider this one is equals to 10, for example using our pink color, I think if we consider the 10, then if this is our minus 40, if this is our plus 40, then our functions look like this one 0, then after that we are getting the similarity. We compare with this, we see this function in Google plot, this kind of function we see. Okay, so we can conclude one thing here, we can simply conclude one thing here, our this is actually our this thing is actually our, what will take this thing actually our distance, and this thing is our kernel. So simply our dissimilarity is same kind of distance here, and our similarity function same thing as our kernel function. You see from here, similarity is kernel, actually for kernel ones, not KNN and kernel, don't be confused. It is kernel. Kernel means what? Kernel? RBF. Okay. So this thing are same as KNN. This both the thing is same in KNN. Okay. Just I am again discussing by using simple picture. Just see if it is our distance line. If this is our distance line, and suppose first let's take, if we consider sigma is equals to 1, so it is 0. We see that here kernel is so maximum 1, kernel is 1 here. If we simple for sigma is equals to 1, we are considering here this point, this NBD's point, that is 4 minus 4. Here we are considering this NBD's point. We are simple, we are considering this point, and we are avoiding this point. After this point we have not considered. If we simple take sigma is equals to 1, we are just consider this point. Okay, we are simple, we are not taking this point. If we see our sigma is equals to, if we see our sigma is equals to 1, we see this sigma now if we see sigma is equals to 0.1, then what we will see, then we are simple taking the more closer point, means this point. If this is equals to 1 and this is equals to minus 1, we are simply here considering this closer and closer point between this distance. I am not considering this. If our point is lie on this region, then we cannot consider. We are simply considering this small region. Okay, we are not considering this. If we considering this point, sigma is equals to 10, so we are now spreading our data set. 0 here we are not using 40 minus 40. Now here considering this point, we are considering this point. Just it is same as KNN. We are just increase the K. If we increase the K, then we are considering more points. If we decrease the value of K, then we are considering the less number of points. We are considering this point. We are not considering this point. Okay. So here our similarity is greater than 0. Similarity is greater than 0 in this region. For our similarity greater than 0 in this region, our similarity is greater than 0. Rest of the part similarity is less than 0. So means what? This means in this region more points, large, more points. We are considering the more points. Actually, for the 10, we are simply considering the more points in this region. Okay, so this is one kind of, this thing is one kind of, you can consider this thing is one kind of for large K. This is the equivalent to for large K in KNN. Okay, and this thing is equivalent to for small k in KNN. Okay, so you can see, sir, these two things are same as KNN, but why without using KNN? This is so simple. I am using this technique. So the main thing is the time complexity. So we see in KNN, if you just remember KNN, if you just remember KNN, if you just remember KNN, we see that if we just training our data using KNN, we have to store all the K points. We have to store all the K points. Okay, this is the, we have to store all the K points. In KNN, we see that. Okay, and simply this time complexity is order of ND. Means if we have n number of data points and for each dimension is d is the dimension for each data point, then simply this is the nd time. Our runtime, for runtime complexity for KNN, we see that it is order of nd, means it is so large number. If our data set is so large and data dimension is large, so it is a huge time taking matter. But if you consider, just if you consider KNN, sorry, RB, radial basis function SVM, if you see, we see that easily we can build the low latency model. Here we cannot consider all the problem, all the point. Here just we are considering the support vectors. Here we are simple considering here support vectors, and for support vectors and corresponding support vectors and its corresponding what alpha is. Okay, only support vectors alpha height we are considering, not all the point. And we know that we know that our support vectors, we know that our support vectors are much and much lesser than our main data point. Because simple, here is just if you see, if you just draw a picture, if you just have pi plus plane, and if your data set is more and more large and data point will be here, only fewer data point will pass through our optimal optimal plane. Only fewer data point is plus. Just here for RBF we are considering this point only. Here in RBF we are not considering this point. All the points we have not considered. This point we are not considering. Only we are considering this support vector. So because of this, the time complexity, we can easily reduce our time complexity for RBF SVM dramatically. Okay, because of this reason, this RBF SVM is so important. And you just remember in the dual problem we have discussed how to use a query point to calculate our YQ. To calculate our YQ, how we used. Simple, it is depend on value of alpha, and we see that for support vectors our alpha is greater than 0, and for non-support vectors, and for non-support vectors our alpha is equals to 0. So if our alpha is equals to 0, then this function is equals to 0. Then this function f of x cube simple 0. And for we have constraint only for support vectors. Because of this, we can easily build a low latency model. But in KNN, our model runtime complexity is so large. Sometimes for a large data set, it is impossible. Okay. So because of this reason, only because of this reason, it is useful. And one thing before finish this lecture, I want to conclude. I want to say just one thing. If we don't know, if for a classifications, if for SVM, we don't know which kernel is more appropriate to a data set, then simply we are using RBF kernel. Okay, it is no, we have to don't remember anything, just we are simply using RBF kernel. If we don't know, the which one is the best kernel, we have to use. Okay, if we don't know which kernel is the best one to our setup, to our classification technique, to our set of data, to our actually those data we are used, which kernel is best one, we don't know. So simple without any doubt we are using here RBF kernel. Okay, we use RBF SBM. Okay, and we see that that in RBM SBM we have to training two parameters. C is for soft margin and simply sigma is for RBF. We have two parameters. Now if we use the RBF kernel, we have to tune these two parameters, and we already know how to tune two parameters. Simple, we have our some techniques called grid search. This is our most simple technique. Grid search, random search. We already discussed this thing in the logistic regression. Okay, by simply using this technique we can easily find our best parameters. And also we see our two hyperparameters also tuned in logistic regression. Just if you just remember our logistic regressions if you just remember logistic regression, then we have elastic net. So in elastic nets also we are using lambda 1 and lambda 2 parameters. This one for our L1 regularizer and this one is for our L2 regularizer. We also see how to choose the two parameter in elastic layers by simply using grid search, random search. So both the same thing is doing here. Both the same thing we are doing. So this C is coming from what? Soft margin, and this sigma is coming from what? RBF function. Okay, I think till now all the thing is clear, all of you. What is importance of radial basis function and how it is important and why it is most popular, why we can use this kernel in general purpose, and how this kernel RBF kernel is same as KNN, k-nearest neighbor technique, and why we are not using KNN as most popular one, but why we used RBF, this most popular one among all of these. So I think you got all the answers from this lecture. If you have any problem, please comment below, then I will here to answer you. Okay, thank you.